In this lecture, we'll look at two very important concepts in control. These are called controllability and observability. Before we start on those two important concepts of controllability and observability, let us quickly recap and see what we have discussed till now. So in the last lecture, we looked at the stability according to Lyapunov and the direct or the second method. In that approach, we basically need to find a positive definite function v of x, where x are the state variables, such that the derivative of v of x, time derivative of v of x, is negative definite. And according to Lyapunov, if such a positive definite function and a negative definite d by dt of v of x exist, then the system is stable. Then the state equations x dot equals f of x comma t is stable. This existence of v of x such that d by dt of v of x is negative definite is a sufficient condition. The Lyapunov direct method cannot be used to show instability, and for a linear single input single output system, the characteristic polynomial of f can be used to obtain the condition for stability and instability. F here stands for the state equations x dot equals fx plus gu. In the basic concept of control or feedback control, we have shown that a system can be made to follow a desired trajectory by using feedback control. So a key question is, when can this be done? This leads to the concept of controllability. And as we have seen in feedback control, we need to make measurements of the output using sensors. Most often, all states are not measured and are available for feedback. It requires too many sensors, and it also increases the cost of the system. So hence, if only some measurements are available, can the system be still controllable? And the conditions under which a smaller set of p measurements, where n is the dimension of the state space and p is the number of measurements that you are doing, is the topic of observability. Okay, so under what conditions we can get away with making less measurements and still do feedback control and achieve the goals of control, that is the topic of observability. There are very few results for general nonlinear systems that are available. Okay, most of the time, or most of the results are for linear time invariant systems. And just to recap, a linear time invariant system is one which is given by these two equations. So we have the state equations, which is x dot is fx plus gu, where x is an n-dimensional state vector and u is the input, which could be m-dimensional. And then we have the output equation, which is y equals hx plus ju, and y could be p of them. It's a p-dimensional vector. So let's look at a definition. A system x dot equals fx plus gu, x element of Rn and u element of Rm, is said to be state controllable if it is possible to transfer any state x of 0 to any desired state x of tf in finite time. Okay, that is the important part. So I want to take the system from x of 0 to some x of t, but in finite time tf. And how can we do that? We want to transfer from x of 0 to x of tf by application of u of t. Okay, so u of t is the input, x of 0 is some initial state, x of t is some final state, I want to go from x of 0 to x of t in finite time tf by applying u of t. Likewise, a system is said to be observable at time t0 if every state x of t0 can be determined by observations y of t over a finite time. Okay, so any state at some time t0 can be determined by observations y of t over a finite time. These are two very important concepts in control using state space formulation. So pictorially, what is happening is we have a state space which is n-dimensional. I want to go from x of 0 to some x of tf. So this is the trajectory. It could be some arbitrary trajectory. And what is x of t? This is that state transition matrix. So it is phi of t comma x0. Okay, so this is the solution of the state equations in using the notion of a state transition matrix. And a system is said to be controllable if I can go from x of 0 to this final x of tf and in finite time. Likewise, a system is said to be observable if I can obtain x of t0 at some time t0. I can obtain x of t0 by observing y of t over a finite time. So let us consider a simple case where f is diagonal and we have a single input. So basically the dimension of G is n cross 1. So then what do we have? The state equations are xi dot is lambda into xi plus gi into u. Okay, so remember u is 1, it's a single input. X are the state vectors I equals 1 through n, and f is diagonal. So the diagonal elements are lambda 1, lambda 2 and so on. So what do we have here? We have a single equation, non-homogeneous equation. So the solution of this equation is xi of t is e to the power lambda I t xi0 plus e to the power lambda I t integral 0 to t e to the power minus lambda I tau g of u tau d tau. So we have seen this. So whenever we have a single non-homogeneous first order differential equation, the solution has one part which is from lambda I xi, which is this homogeneous part, and then there is one part which is due to this u, which is the non-homogeneous part. Okay, so this is like a convolution, and this is the solution to the homogeneous differential equation. So a system is said to be state controllable if and only if there exists a solution to this above equation. Okay, or in particular, if you substitute t is tf and then you take this to the left hand side, so we have xi of tf minus e to the power lambda I xi of 0 is equal to this rest of it, which is e to the power lambda I tf plus 0 to tf e to the power minus lambda I tau gi u tau d tau. Okay, so I want to go from 0, xi of 0 to xi of tf in finite time. So then if that is possible, then there must be a solution to this equation. Okay, and what we can clearly see is if gi were to be 0, then there is no solution. Okay, so I can only go from xi of 0 to xi of tf as long as this gi is not there, is non-zero. Okay, because if gi were to be 0, then whatever I do to u, it's not going to change the states. Okay, the states are disconnected from the input u. If f is not diagonal but has distinct eigenvalues lambda I equals 1 through n, then we can transform the state equations using x equals pz, and we have done this before. I can write the state equations as z dot is equal to p inverse f pz, plus P inverse GU, or we have a diagonal matrix lambda 1, lambda 2 all the way till lambda n, and all other elements are 0 into Z, plus P inverse G is nothing, we can write it as some F1, F2, Fn. Okay, so the elements of P inverse G are these numbers or scalars F1 through Fn. So as you can see, for a single input, single output system, why? Because U is only single input here. The state controllability implies that no elements of P inverse G, which is F1 through Fn, can be 0. So if, for example, the kth element, let's say Fk somewhere here is 0, then U will not influence Zk, because that equation will become Zk equals lambda k into Zk plus 0 into U. Okay, so by application of U, I will not be able to change the states of the system. I will only get the natural dynamics, whatever is lambda. So Z will be a function of e to the power lambda k into t into Z0. Okay, so this is another way of intuitively looking at what is controllability. No element of this P inverse G can be 0. If F does not have distinct eigenvalues, then it becomes a little bit more complicated, but nevertheless the idea remains the same. We can again obtain a P such that P inverse Fp is this Jordan canonical form of this matrix F. Okay, so again we transform x equals pz. Again we get z is P inverse Fpz plus P inverse Gu. Now instead of this being a diagonal matrix, we have a Jordan canonical form, and we can say that this system is state controllable if and only if no two Jordan blocks of Fj are associated with the same eigenvalues. The elements of any row of P inverse G that corresponds to the last row of each Jordan block are not zero, and elements of each row of P inverse G that corresponds to distinct eigenvalues are not zero. So this one which corresponds to distinct eigenvalues non-zero is same as what we discussed earlier. So if any of the elements of P inverse G corresponding to distinct eigenvalues is 0, then that state variable is not affected by U. However, if you have a Jordan block, then it's a little bit more complicated. So if you think about it, the second condition, that elements of any row of P inverse G that corresponds to the last row of each Jordan block are not 0. That is sort of obvious. Okay. So as an example, let's consider two repeated lambdas, two repeated eigenvalues. So this is a 3 by 3 system. So the matrix F is 3 by 3. We have Z1 dot, Z2 dot, and Z3 dot. So Z1 is given by minus 1 Z1 plus 1 Z2 and 0 times Z3. So Z2 dot is 0 minus 1 into Z2 plus 0 into Z3, and Z3 dot is minus 2 into Z3. And what you can see here in the U, GU, that is 0, 4, 3. So this 0 is still okay because this is the Jordan block. Okay, and the last row of the Jordan block, this cannot be 0, this one can be 0. And the fact that this last equation, which corresponds to an eigenvalue of minus 2, this 3 cannot be 0. Okay, so so this is an example of two repeated lambdas. So the two repeated lambdas gives this Jordan block, and the third lambda is minus 2, which is distinct. So hence in this Jordan block I can have one 0 here, but the second one cannot be 0. So now let's get back to the original state equations, which is x dot is equal to fx plus gu. The solution to the state equation can be written as x of t e to the power ft into x of 0 integral 0 to t e to the power ft minus tau g u tau d tau. And let us now for the moment assume that the final state is the origin of the state space. So the final is 0. Okay, so 0, 0, 0 and so on. And we want to transfer from some initial x of 0 at t equals 0 to the origin in time tf. So for the above, x of t1 is 0, okay, and e to the power f. So this 0 is now equal to e to the power ft x of 0 integral 0 to t1 e to the power f t1 minus tau g u tau d tau. So remember, I want to go from x of 0, which is my initial state, to the origin. This is just a simplification and to bring out an important concept, which we will see very soon. So the above equation implies that if x of 0 is minus 0 to t1 e to the power f t1 minus tau g u tau d tau. Okay. So you take to this side and then you do, so then you will get a minus sign, and then you can simplify and write x of 0 is this. E to the power minus f tau can be written as a minimal polynomial. Okay, this is basically the Cayley-Hamilton theorem, which says that a matrix satisfies its characteristic polynomial. So e to the power f tau is some I plus f square ft into f squared t squared divided by factorial 2 and so on. So that infinite series can be represented as a minimal polynomial I equals 0 to n minus 1 some alpha I tau into f to the power I. Okay, so this is the idea of a minimal polynomial, which we have seen earlier when we wanted the solution of or how to find the state transition matrix. The concept of a minimal polynomial was introduced, and this is the same idea from there. So hence x of 0 can be written as this polynomial with a minus sign into integral of 0 to t1 alpha I tau u tau d tau. Okay, so all we are doing is we are writing e to the power minus f tau, which is here, okay, right, in this polynomial form, and then substituting that e to the power minus f tau here. So we are left with some fi, f to the power I, g, which we can take it outside, and then you have 0 to integral 0 to t1, okay, alpha I tau u tau d tau. Okay, so you can see that is all we are doing is we are simply substituting this in this equation. Okay. So in the previous slide we had one integral 0 to t1 alpha I tau u tau d tau. So let us denote that integral by beta I. Okay, so for each alpha I we have one beta I. So now we can write this x of 0. Okay, so remember we start from some initial x of 0 and we want to go to the origin. We can rewrite that previous expression for x of 0 as minus, and there's a matrix here. I will go over it slowly. This first column is G. Remember we are discussing G as n by 1 and F is n by n. So we have n by 1 a column here. Then the next column is F into G. The third column is F square into G. And the last column is f to the power n minus 1 into g. So since this is a n by 1 vector, f into g is also an n by 1 vector, and all of these columns are n by 1 column vectors. So this matrix here fully is a n by n matrix. So we can write x of 0 as some n by n matrix into beta 0 all the way till beta n minus 1, another column vector. So basically what we have is, if I call this a matrix A, so we have A into beta will be equal to x of 0. So for complete state controllability for any x of 0, any initial state which we want to take to the origin, the n by n matrix A, which is nothing but this quantity here, G, Fg, f square g, and so on all the way till f to the power n minus 1 g, okay, which is denoted now by this qc, which is sort of like minus a, okay. So then this qc matrix must have full rank. Why? Because we have some equation like ax is equal to b, okay. So b is some arbitrary vector. Okay, so for any solution of this to exist, that means if I need to solve this linear equation ax equals b, okay, so the rank of this matrix A must be n, because this is n by 1, beta is also n by 1, so this must be full rank. Okay, so that is what is mentioned here. So the rank of this matrix G, f into g, and so on must have full rank. So this derivation that a system is state controllable if this matrix called QC, which is G, Fg all the way till f to the power n minus g has full rank, was obtained by Kalman in 1960. He introduced this concept of this controllability matrix QC, and he derived this result. So till now we have assumed U is single input. It can also be extended to multi-input case where U is an m-dimensional vector. Okay, so it is an element of Rm. So for U Rm, QC will have dimension n cross nm. Okay, and the rank of QC must be still n for state controllability. So what is n? N is the number of state variables. N by n is the dimension of the matrix F. G has the, if it is m dimensional, okay, then the dimension of QC must be n cross nm, and the rank of QC must still be n for state controllability. So now we have two statements for controllability. So let's call the first one a statement A, which is the following, which is the very basic definition of when is a system state controllable. So statement A says the following: a system f comma g is controllable if there exists a control input u of t such that any initial state of the system x0 can be taken to a desired final state x of tf in finite time interval t of tf by the application of ut. Okay, so it's a very basic definition of a system being controllable, that I can go from any initial state to another desired final state in finite time by applying the control input u of t. In the previous slide, I also showed you another version of when a system is state controllable. So let's call that statement B. So the system f comma g is controllable if and only if QC has rank n. And what was QC? QC, the first column was G, the second column was f into G, the third column was f square into G, and so on all the way till f to the power n minus 1 into G. So QC is of dimension n cross n. So the second statement was, which I discussed in the last slide, the system is state controllable if the rank of QC is n. So now let us prove that statement A and statement B are same. Okay, this is one way of defining what is a controllable system. This is another way of defining a controllable system. This is the definition or the derivation according to Kalman, and this is a very basic notion of what is something which is controllable. So let's start with the proof. So first is we will prove that A implies B, and then we will say B implies A. So then A and B are identical if we can show both directions. So let's start. So we assume F and G is controllable. Okay. So we'll assume statement A is true, but then we assume that statement B is not true. So basically we will show that if you assume F and G is controllable and then we say that rank of QC is less than n, we will say that this is not true. This is false. So hence A will imply B. So we first want to assume the opposite and we show that the opposite is not true. So this is a very standard way of proving some theorems in maths. Okay, if you want to say A implies B, then we assume A to be true and then say that okay, B is not true. Something in B is not correct or not valid. And then we go through the steps and show that this assumption is not correct. So hence A implies B. So that is the basic idea. So we assume F and G is controllable, but rank of QC is less than n. Okay. So if rank of QC is less than n, there exists a vector in the null space of QC, right? So QC, if it is, say, rank is less than 3, okay, I'm assuming n is 3, then there will be a vector in the null space of QC. The null space of QC will be one dimensional if the rank is 2. Okay, so the basic idea is that if the rank of QC is less than n, there exists a vector in the null space of QC. This is a very basic result from linear algebra. So if there is a vector in the null space of QC, then V dot G. So remember, G is a column vector and V is that vector in the null space. So V dot G, then V dot F square G and all the way till this should be equal to 0. So hence, by Cayley-Hamilton theorem, we know minus f to the power n is some a1 f to the power n minus 1, a2 f to the power n minus 2 and so on, plus ani. So Cayley-Hamilton theorem, if you recollect, is that the matrix satisfies its characteristic polynomial. So we have a1 to the power some function of characteristic polynomial, so lambda to the power n plus something into lambda to the power n minus 1 is plus all the way till something constant is equal to 0. So instead of lambda we substitute f for lambda and we get one polynomial in f to the power n plus something into f to the power n minus 1, something into f to the power n minus 2 and so on, all the way till identity equal to 0. And then you take the f to the power n on the other side, so we'll have minus f to the power n will be equal to all these other terms. So now if you take a dot product minus v dot f to the power n into g, we will get a1 into v dot f to the power n minus 1 into g. So what have we done? We are using this result from Cayley-Hamilton theorem. We are multiplying by v dot f to the power n g, and then we substitute all these things and you'll get a1 into v dot f to the power n minus 1 g plus a2 into v dot f to the power n minus 2 into g and so on, all the way to a n into v dot g equal to 0, right? So this equation, right hand side you multiply by g and left hand side you do v dot. That's all we are doing. So by induction now, v dot f to the power n plus k into g is 0. Okay, so for k equals 0, 1, 2, or all the way till infinity, or v dot f to the power m into g is 0 for m equals 0, 1, 2, 3. Correct? Because we have v dot f to the power n into g is 0. So then by induction we assume using induction we can show that v dot f to the power n plus k into g is equal to 0, and then we rewrite this n plus k as m, and we write v dot f to the power m into g equal to 0. So hence v dot e to the power ft into g, which is v dot I plus ft plus f squared t square into 1 by factorial 2 all the way is equal to 0. Right? Because from this step. Okay, so think about it. We have proved that v dot f to the power m is equal to 0. So then we can write v dot e to the power ft into g. And what is e to the power ft? This is all these quantities into g equal to 0. So for 0 initial conditions, x equals 0, the solution to the state equation is x of t 0 to t e to the power f t minus tau g u tau d tau. So hence v dot this right hand side is now equal to 0. So this implies all points reachable from origin 0 are orthogonal to v, because these are the points which are reachable from origin. Okay, so we start from x equal x of 0 as 0, then x of t is the solution of the state equation, which is the first term will go to 0 and we are left with only 0 to t e to the power f t minus tau g u tau d tau. Okay, so you can go back and see the solution x of t. It is one part which is the initial first or the initial condition, which is x of 0 into e to the power f t plus the particular part. Now x of 0 is 0, so we are left with x of t. And then we can take a v dot of this, and then it is clearly equal to 0, because that is what we proved in the previous slide. So hence all points reachable from the origin are orthogonal to v. So v is some vector and this is another vector, and all these points are x of t are orthogonal to v. So which basically means some points in the state space x of element of Rn cannot be reached. Okay, so because v dot of this equal to 0. So think about it. I have showed you that I start from origin and this is the solution to the state equation, and then there is a vector v which is in the null space of QC. Okay, and that v dot, then this quantity is 0. So which basically means that there are some points in the state space which I cannot reach, because that is orthogonal to the solution. Okay, hence f and g is not controllable. But we started with the assumption that f and g is controllable. Okay, so hence this is a contradiction. So this is a proof by contradiction. So hence statement A implies statement B. Okay, so what did we start with? We assumed statement A was true, and we assumed that statement B was false, that the rank of QC was less than n. And then I have shown you that this cannot be true. If f and g is controllable, then the rank of QC cannot be less than n. Okay, so hence A implies B. Now we will continue and show you that the B also implies A, and hence statement A and B are identical. It's a very useful thing to remember. I mean, it is a little bit complicated and little bit math and logic, but statement A is a very basic definition of a system being controllable. Statement B is something which Kalman derived, and at least till now I have shown you that A and B are similar in the sense that A implies B. So let's do the backwards, that B implies N, A. So basically what do we have? We assume that the rank of QC is N, but the system F and G is not controllable. Okay, we start with this assumption and we will show that this is false. Okay, that there is a contradiction. Okay, similar to last time. So if system is uncontrollable, it implies that some V dot this solution of the state equation will be equal to 0 for some non-zero V. Okay, if the system is not controllable, then there are some points which I cannot reach. And there is a vector V in the null space such that V dot that solution x of t is equal to 0. So then we can show this implies that V dot e to the power f tf minus tau into g is 0. Okay, so for some 0 tau less than or equal to tf. So for t tau equals tf, V dot g will be 0. Then taking the derivative of V dot this equal to 0 and setting tau equals tf, we will have V dot f into g is equal to 0. And on similar lines we have V dot f square g, then all the way till V dot f to the power n minus g equal to 0. Okay, so this contradicts the assumption that QC has rank n. Remember what is QC? The first column was G, the second column was F into G, the third column was F squared G, and all these columns are linearly independent. Okay, but what, so, or that QC has rank, okay, n. But we are showing that there is a vector V such that V dot G equal to 0, V dot Fg equal to 0, V dot F square G equal to 0, and so on. So hence there is a some non-zero V such that this system, I cannot reach that. Okay, the solution x of t dot V is equal to 0. So which basically contradicts the assumption that QC has rank n. So we started with assume QC has rank n, but the system is uncontrollable, and I showed you this contradicts that assumption. Okay, so hence statement B implies statement A. So again, what was statement A? That was the very basic definition of controllability. A system f comma g is controllable if there exists a control input u such that any initial state of the system x0 can be taken to a desired final x of t, okay, in finite time interval t of tf by the application of ut. And this is the definition. Statement B is what is derived by Kalman, and he said the system f comma g is controllable if and only if QC has rank n. And what we have shown you that these two statements are exactly same. Okay, it's a long proof, but it is important to realize that the very basic definition of controllability of a system f comma g is the same as something which is very easy to figure out. We can always find out what is QC. First column is G, second column is FG, and so on. And to obtain the rank of that matrix is also fairly straightforward. So instead of looking at this sort of little bit abstract definition, we can easily check if a system f comma g is controllable just by checking the rank of QC. And both these definitions I have proved to you mean the same thing. There is also something called output controllability. Often the output of the systems need to be controlled, not the state. Okay, so if you consider this linear time invariant system x dot again fx plus gu and y equals hx plus ju, the above system is said to be completely output controllable if it is possible to transfer any initial output y of 0 to final output y of tf. Okay, so and in finite time by the application of u of t. So we are not really interested in going from x of 0 to x of tf. We are more interested in going from y of 0 to y of tf by applying u in finite time tf. And it turns out that system is completely output controllable if and only if the p cross n plus 1 m matrix H, G, H, F, G, H, F to the power n minus G and appended with the J matrix has rank P. Okay, so remember there are Y is Hx plus Ju, the dimension of Y is P cross 1. So we are making P measurements out of the available n states, and then we can obtain a matrix which is now must include H, F and G and also J, and in this form. So the first part is H into G, then H into F into G, then you concatenate these two, and then all the way you concatenate H into F to the power n minus G and finally J. Okay, so this complicated looking matrix must have rank P. Okay, I will not go into the proof of this, but this is what output controllability means. In output controllability, you can see that there is also a term which is J. Okay, so what was J? J was the direct term. There is a connection directly from U to the output. So if you have a direct term J into U, this helps in output controllability. So let us continue. We also mentioned that there is a very important concept in control which is called observability. Okay, so let's go into a little bit more detail. So consider an LTI system which is again x dot equals fx plus gu and y equals hx plus ju. So as mentioned in the past, often all the states x are not measured and only y, which is element of Rp, where p is less than n, are measured. So the measurements y provide partial information about the states. So remember, p is less than n. So the basic notion of observability is the following. A system is said to be observable at time t0 if state x t0 can be determined by observations y of t over a finite time tf given f, g, h and j and ut. Okay, so I want to know what is the state, okay, x of t0 by measuring y of t, but remember the number of measurements y of t, which is p, is less than n. So from the output equation, h into x at t0 will be y at t0 minus j into u of t0. Okay, so this is n by 1. H is p by n. Okay, so the dimension of h is p by n with p less than n. So hence there are less number of equations than unknowns. Okay, what are the unknowns? X of t0. So there are n unknowns, but the number of equations is only p. So how do I find out these n unknowns when we have only p equations? So there are infinitely many possible solutions from linear algebra. Okay, so it is like ax is equal to b. Okay, so the dimension of x is n, but a is not n by n. So we have infinitely many solutions. So what can we do? We can use the time history of y of t and u of t to obtain the x of t0. So once x of t0 is known, okay, any xt is also known. Why? Because the solution to the state equations are known. So what is the solution? X of t is some e to the power ft into x of t0 plus some integral, that convolution term. So if I know what is the initial conditions x of t0 at t0, then I can use the state equations to find any other xt. So before we go into the formal way of approaching observability, let's quickly see under what conditions a system is not observable. Okay, so we will take some simple cases. So first is we look at an LTI system, linear time invariant system with j equals 0. So then we have the state equation is x dot is fx plus gu, and we have y equals hx. So let us now, like in the past, do a transformation from x to z, which is x equals pz, and then convert this f into a diagonal form. So we are looking at a very simple subset. Okay, so in the diagonal form we will have z dot is some diagonal matrix with lambda 1, lambda 2 all the way to lambda n into z, and then we'll have some p inverse gu. The output equation can be written as y is equal to h into pz. So remember x is pz, so x is pz. So we'll have h into p into z, and let's call this h into p as h tilde. And what is h tilde? So z is n by 1, so there are n columns, and let's call them h1 tilde, h2 tilde all the way till hn tilde. Okay, so where hi tilde are the columns of this matrix h tilde. So what you can clearly see is that for observability, no column of this can be 0. Why? Because the first column is into z1, second column into z2. So y is h1 tilde into z1 plus h2 tilde into z2 and so on. Okay, so this is a very intuitive way of looking at when a system is not observable. So if any of these columns are 0, then that z, say let's say the kth column is 0, then zk into 0 will not show up in y. Okay? There will be no connection between y and zk. So now let's go back to the basic idea that we want to use the time history of y and u of t, and of course we want to use it only for a finite time tf, okay, and see whether we can obtain the initial condition x of t0. Okay, so we have n measurements, y of 0, y of n, all the way till y of tf. Alternatively, we can estimate the derivatives y of t, y dot of t, and so on. So what is y dot of t? Which is y1 minus y0 divided by t1 minus t0. So I want to estimate the derivatives of y of t. So y dot is like this. How about y double dot? That also we can find out. So basically we can use some kind of a finite difference. So y double dot will have y2 and then y1, and y of 0, and then it will have t2, t1 and t of 0. Okay, so all the derivatives up to y to the power n minus t can be obtained from these n measurements. So now let's go back and see the output equation with j equals 0. So we have y of t is h into x of t. So the derivative of the output equation y dot will be h into x dot. Remember, h is a constant matrix. Now x dot is same as f into xt plus g into ut. So if you go back and substitute x dot from the state equations, we will get h into f into xt plus h into g into ut. So we will have this. So I want to write this as y dot of t as h into f into xt plus c1 of t. Why? Because this is known. We know what is h, we know what is g, and we know what is u. Okay, so when you are giving u, so the time history of y and ut are known. So for every given ut, I know what is the output y. So I can rewrite this expression as y dot is h into f into x of t plus c1 of t. From the second derivative also I can write y double dot is h into f square x of t plus h into f into g u of t plus h into g into u dot of t, and again we know what is u dot of t. U dot of t is u of t1 minus u of t0 divided by t1 minus t0. So hence I can write all these terms as some c2 of t. So I have y double dot as h into f square, which is this term, into x of t plus everything else under c2 of t. And finally I can write y to the power n minus 1t. So the n minus 1th derivative of y of t as h into f to the power n minus 1 x of t plus all these terms, which can be again clubbed together as c into n minus 1t. Okay. So since the time history of ut together with f, g, h are known, all the ci's are known. So we can rearrange all those equations as y of t, y dot of t, y double dot of t, so these are in one below the other, is equal to h into xt plus c0, h into f into xt plus c1, and all the way to h into fn minus 1 xt plus cn minus 1. So this is like a expression which is y equals some matrix times x of t plus some constant. So this above equation can only have a solution if and only if this matrix here, h, hf, hf square, h to the power fn minus 1 is a full rank. Now instead of writing it in this form, we are going to write it in this form, which is h transpose then appended with f transpose h transpose, then appended with f transpose square into h transpose, and all the way till f transpose to the power n minus 1 h transpose. So this is a matrix which is exactly the same as this. It is written in a form such that it can fit into a line. So this matrix is called Q0 or QO, which is the observability matrix. So the rank of this matrix here, or QO, must be n. Only then this equation can be solved. Okay, so this equation, which is something like y equals ax plus b, will have a solution only if the rank of this matrix A times x, the rank of A has n, is full rank. So this is another of Kalman's derivation, and he obtained this expression for this observability matrix again in 1960, and he showed that a system is observable if the rank of this QO is n. Okay, and remember what is observable? I can find the states by measuring output y. However, the number of outputs that I am measuring, which is p of them, is less than the number of states, which is n of them. We can also extend the same results if you have multi-input case, if you have m inputs instead of single input, which is what is shown here, and that has been done. So in summary, the controllability and observability are two very important and useful concepts in modern state space control. A system is not state controllable if U does not affect a state. A system is not observable if Y is not connected to a state. Okay, that is very intuitive and very basic. Kalman found two matrices QC and QO. Okay, and if the rank of those matrices are n, where n is the dimension of the state space, then we can say that the system is controllable or observable. Okay, and this controllability and observability matrices are used extensively for design of controllers using state space approach. We will see that later on in this course. Unfortunately, there are very few results available for general nonlinear systems. Okay, this is well known and well extensively studied and extensively used for linear systems. Not very nice or general results are available for nonlinear systems.